NetCore and Entity Framework empower developers to build robust, scalable applications. A deep understanding of these technologies is essential. This guide is your roadmap to interview success. Interviewers seek candidates who can apply their knowledge. Your path to success starts now. Senior-level interviews assess your technical acumen and problem-solving abilities. Expect questions on object-oriented programming, design patterns, and database interactions. Interviewers challenge you to apply your understanding to real-world scenarios. They assess your ability to write clean, efficient, and maintainable code. Emphasis is on solid principles. Another crucial aspect is asynchronous programming. Be proficient in using async and await keywords. Object-oriented programming, OOP, is a cornerstone of modern software development. .NET Core fully embraces OOP principles. Understanding OOP is crucial for senior-level interviews. It helps in building robust, maintainable applications. The 4 pillars of OOP are encapsulation, abstraction, inheritance, and polymorphism. Mastering these is essential for any senior-level .NET Core developer. Let's delve into encapsulation with a banking application in .NET Core. You'd have a class named Bank Account. The account balance should be private. Define public methods like deposit, withdraw, and get balance. This ensures data integrity and security. Encapsulation is key in OOP and .NET Core. Abstraction and encapsulation provide higher organization and flexibility. Imagine building an e-commerce app in .NET Core. You have various payment methods like credit cards, PayPal, and Apple Pay. Abstraction defines a common interface for payment processing. This promotes code reusability and maintainability. Adding new payment methods becomes simpler. Abstraction is key to maintainable software design. Understanding and applying solid principles is paramount for senior-level .NET Core development. These principles guide you in crafting functional, maintainable, and extensible software. SOLID stands for Single Responsibility, Open-Closed, Liskov Substitution, Interface Segregation, and Dependency Inversion. Each principle promotes modularity, reduces dependencies, and simplifies your code base. Mastering these principles is essential for any senior-level .NET Core developer. Applying these principles ensures a robust, maintainable, and less buggy codebase. The Single Responsibility Principle, SRP, lies at the heart of writing modular and maintainable code. SRP states that a class should have one reason to change. Refactor classes into smaller, focused ones. It improves readability and maintainability, reduces impact of change, and promotes testability. The Open-Closed Principle, OCP, encourages designing code for extension without modifying existing code. Imagine developing a reporting module. Initially, you have a sales report and a report generator class. To follow OCP, introduce an iReport interface. Report classes implement iReport, and report generator depends on it. This makes your code flexible and extensible. In software development, certain challenges arise repeatedly across different projects and domains. Experienced developers have identified elegant and reusable solutions, known as design patterns. Design patterns are time-tested concepts that guide code structuring. Think of them as blueprints for solving common software design problems. Mastering design patterns is crucial for senior-level .NET Core developers. In .NET Core, certain patterns are particularly relevant. These include the repository, unit of work, dependency injection, and factory patterns. Applying these patterns enhances code quality and maintainability. The repository pattern helps decouple your application logic from the data access mechanism. It provides an abstraction layer, allowing consistent data interaction regardless of the technology used. Imagine building an e-commerce app with Entity Framework Core and SQL Server. Without it, your code is tightly coupled, making future changes difficult. The pattern introduces an interface like iProduct Repository for operations on product entities. Implement this interface with a class like SQL Product Repository using Entity Framework Core. This decoupling makes your code more testable and flexible. Switching to a different ORM or data store only requires a new repository implementation. The repository pattern is essential for building maintainable .NET Core applications. Unit of Work Pattern: streamlining transactions, ensuring consistency. The Unit of Work pattern works with the repository pattern to streamline transaction management and ensure data consistency. It tracks changes to multiple entities within a single transaction and ensures atomic persistence. Imagine a shopping cart checkout process in an e-commerce app. Multiple operations like creating an order and updating inventory are involved. If any operation fails, the transaction rolls back to maintain consistency. The Unit of Work class acts as a container for all changes within a transaction. It exposes methods like begin transaction, commit, and rollback. This pattern ensures data consistency and reduces the risk of data corruption. Enhancing responsiveness and scalability. The power of asynchronous programming. Responsiveness is paramount in high-performance applications. Users expect snappy applications, even with time-consuming operations. Asynchronous programming in .NET Core allows operations to run in the background. Imagine fetching data from a remote API. Synchronous approaches block the main thread. This freezes the user interface, frustrating users. Asynchronous programming initiates API calls without blocking. The application continues processing, providing a seamless experience, essential for high-performance, scalable applications. Enhances user experience and maximizes resource utilization. Mastering async and await. A deep dive into asynchronous operations. Fetch data from a RESTful API in .NET Core. Using the HTTP client class, the getString async method is asynchronous. To make this code truly asynchronous, leverage async and await. Reap the benefits of responsiveness and scalability. Dependency injection, or DI, is a core feature of ASP.NET Core. It promotes loosely coupled, maintainable, and testable code. Imagine a service class that depends on a data access class. Without DI, it creates its own dependencies, leading to tight coupling. This makes testing difficult and the code less flexible. DI inverts this dependency, providing dependencies from the outside. ASP.NET Core's built-in DI container manages and resolves dependencies, making your code cleaner and more modular. This centralized management promotes code reuse and flexibility, allowing easy swapping of implementations. In ASP.NET Core's DI system, services are registered with a specific lifetime. Choosing the appropriate lifetime is crucial for your application's efficiency. Let's delve into transient, scoped, and singleton lifetimes. Transient services are created each time they are requested. Scoped services have a lifetime scoped to a single client request. Singleton services are created once and shared across all requests. Choosing the wrong lifetime can lead to bugs and performance issues. Understanding service lifetimes is essential for efficient ASP.NET Core applications. When working with an ORM like Entity Framework Core in .NET Core, understanding how to efficiently load related data is crucial. Imagine you're building an e-commerce application with products and categories. To display product details with category names, you need data from both products and categories tables. EF Core offers three primary data loading strategies: eager loading, lazy loading, and explicit loading. Eager loading fetches related data in a single query. ideal when you always need the related data. Lazy loading defers data loading until accessed, useful for large datasets but requires careful consideration. Explicit loading gives fine-grained control, letting you decide when to load related data. Understanding these strategies and their trade-offs is key for building efficient .NET Core applications. Section 2. Eager loading. Retrieving related data in one go. Eager loading is the preferred strategy when you need related data for most entities. It minimizes database queries, improving performance. Let's revisit our e-commerce example. Display a list of products with their category names. Eager loading fetches category data with product data in a single query. It avoids the N+1 query problem, improving performance. Use eager loading wisely to avoid loading unnecessary data. In summary, eager loading optimizes data retrieval by loading related data upfront. Middleware is the unsung hero of ASP.NET Core request processing. It acts as a crucial intermediary between an incoming HTTP request and your application's logic. Middleware components inspect, modify, or short-circuit requests before they reach your controllers. This modular approach allows for powerful and customizable request processing pipelines. Each component performs specific tasks like logging, authentication, or caching. Middleware is composable, enabling sophisticated request processing workflows. Requests flow through middleware in the order they were added. Components can pass requests along or generate responses directly. Understanding middleware is essential for building robust ASP.NET Core applications. Section 2. Use routing. The director of traffic in your application. In the realm of ASP.NET Core middleware stands out as a pivotal component, directing incoming HTTP requests to their intended destinations. It's the traffic cop of your application, ensuring each request finds its way to the correct controller action or Razor page. Routing maps incoming URLs to specific handlers within your application. ASP.NET Core offers a flexible routing system using attributes, conventions, or both. This middleware intercepts requests, analyzes the URL, and matches it against routing rules. Without it, your application wouldn't know how to map incoming URLs, rendering it unresponsive. The challenge of concurrency. Safeguarding data integrity in multi-user environments. In modern web applications, multiple users can access and modify data simultaneously, making data integrity a critical concern. Imagine two users editing the same product record. User A updates the price. User B modifies the description. What happens when both changes are saved? Without proper handling, you risk data loss or inconsistency. This is known as a lost update. Addressing concurrency issues is crucial for data integrity. Optimistic concurrency control. A pragmatic approach to data consistency. OCC offers a pragmatic approach to handling concurrency in .NET Core and Entity Framework Core. Unlike pessimistic control, OCC assumes conflicts are rare and allows concurrent access. It checks for conflicts only when saving changes, making it more performant. The key to OCC in EF Core is the use of concurrency tokens. This token is typically a timestamp or row version number. EF Core stores the token value with the entity's data. When saving changes, EF Core includes the original token value in the update statement. The database checks if the token value matches the current value. If they match, the update proceeds normally. If not, a concurrency conflict occurs. Your application needs to handle conflicts gracefully. OCC balances performance and data consistency. It's suited for scenarios with infrequent conflicts. Architecting for success, laying the foundation for robust applications. A solid architectural foundation is key to building functional, maintainable, and scalable applications. Just as buildings need strong blueprints, software needs a sound architectural vision. Software architecture guides the design and organization of your codebase. It outlines major components, their interactions, and underlying principles. A well-defined architecture promotes modularity and code reusability. This simplifies maintenance and adaptation to new requirements. Common patterns like layered architecture organize applications into distinct layers. Each layer handles specific functionality, enhancing maintainability. Section 2. Domain-driven design. Aligning software with business realities. Domain-driven design, or DDD, emphasizes understanding and modeling the core business domain. It aligns software design with the language and concepts of the business it serves. DDD is a collaborative effort between developers and domain experts. The goal is to create a shared understanding of the domain and express that understanding in the code. DDD introduces key concepts like entities, value objects, and aggregates. Entities have unique identities, like a customer or product. Value objects are defined by their attributes, like an address. Aggregates cluster entities and value objects, like an order and its items. Domain services are stateless operations that don't belong to a specific entity. Using a ubiquitous language creates a code base that reflects the business domain. This fosters better communication and reduces misinterpretations. DDD leads to robust, maintainable, and adaptable software. Section 1. Interfaces. Defining contracts for polymorphic behavior. Interfaces and abstract classes promote code reusability, polymorphism, and maintainability. Understanding their differences is crucial for design choices. Let's start by delving into interfaces. At their core, interfaces define contracts. They outline methods a class must implement. Think of an interface as a blueprint. For example, a drawable object must implement a draw method. This promotes loose coupling and interaction through interfaces. Abstract classes. Sharing implementation, enabling specialization. Interfaces define contracts without implementation, while abstract classes blend both. They can have abstract methods as placeholders and concrete methods with code, suitable for sharing functionality among related classes, allowing specialization. Think of an abstract class as a partially implemented blueprint. It offers common functionality and room for customization. For example, an abstract shape class with calculate area and get perimeter methods. Circle and square inherit shape, implementing calculate area and inheriting get perimeter. Abstract classes enforce constraints across a class hierarchy. Unlike interfaces, abstract classes do not support multiple inheritance. Reflecting on key concepts. Appreciate the breadth and depth of knowledge you've gained. We've explored core principles of .NET Core and Entity Framework. From object-oriented programming to design patterns, you've acquired a robust toolkit. Mastering these is about understanding principles and best practices. Develop a keen eye for identifying and addressing potential issues. Connect the dots and see how principles lay the foundation for modular code. The journey to mastery demands continuous learning and adaptation. The knowledge and skills gained will serve as a solid foundation for your expertise. Embracing the senior level interview. Armed with a comprehensive understanding of .NET Core and Entity Framework, you're well prepared for a senior-level interview. Interviewers seek candidates who demonstrate problem-solving skills, critical thinking, and a passion for software craftsmanship. Approach the interview as an opportunity to showcase your knowledge and enthusiasm. Discuss your experiences, challenges, and lessons learned. Illustrate key concepts with practical examples from past projects. Practice, review concepts, and work through coding exercises. Articulate your thought process clearly. Explain your reasoning and ask insightful questions. Be yourself, be enthusiastic, and let your passion shine through. With preparation and a positive attitude, you can confidently navigate the challenges and secure your dream role.